today's online training session. So my name is Simon Grandin and I'm the photogrammetric workflow specialist here at SimActive. So today the topic of my presentation will be how to calibrate and process multispectral imagery with Correlator 3D 8.5. So basically, maybe most of you may know we've just launched a new version of Correlator 3D 8.5, which include two major breakthroughs. The first one is the data sharing over the web, and the second one is basically the topic of my presentation today, is how to integrate sun sensor and reflectance panel to calibrate the reflectance of your multispectral data. So today, what you will learn in this presentation, I will start with briefly a summary of understanding the different spectral bands that we can have with multispectral data sets. I will also talk about the processing requirements if you want to calibrate your reflectance. Also, I will talk about how to create a project from multispectral data, because as many of you may know, the workflow is quite different than a typical UAV project. So I will show you how you can manage that. I will show you also how to register multiple band throughout the arrow triangulation module. I will show you how you can view the different bands and also do some composite color imagery to see what you can get from those imagery. We'll also talk about performing the reflectance calibration based on the reflectance panel or the sun sensor or both of them. And at the end of the presentation, I will talk about how to export reflectance maps and also vegetation indices such as NDVI. So let's talk about understanding the spectral band that we have with multispectral data. So typical UAV usually comes with three bands, a red, a green, and a blue band, which what we call visible light band. Those are wavelengths that we can see from our with our eyes, and a multispectral dataset usually can add other wavelengths that are not visible with our human eyes. Those non-visible wavelengths or non-visible light, such as the red edge or the near-infrared, gives us a lot of information especially about the vegetation content. And the goal of using multispectral data is to get as much as possible information about the vegetation with those non-visible light wavelengths. So basically, what are the most spectral bands that are available? The RGB are typically for a normal camera, but for most of the multispectral camera on the market, you can have other bands such as the red edge, the near infrared, and also depending on the model of camera that you have, you can have a thermal band, or some of the new sensor can include up to 10 bands on the same scene, which you're gonna have some visible and some non-visible wavelengths. So what we can see in the image below is we can see that the vegetation has a different responses from the visible light than the non-visible light. This is why we usually use non-visible wavelengths to perform some vegetation indices. Typically, the vegetation have a low reflectance in the red and the blue band and a small bump in the green band, which is basically why we're seeing the vegetation green as it is. But when we looked in non-visible light, we can see that the vegetation has a much more higher reflectance, which allows us to compute vegetation indices with a difference from the non-visible and the visible light, let's say such as the NDVI, which is basically the near-infrared and the red. It's a combination of the near-infrared and the red band. And mixing those two information gonna really give me information about the vegetation content of my field. But again, what is the reflectance? So basically, the reflectance is the amount of light that is reflect from a sources depending on the spectral band you're looking at. So, and it's also typically known or expressed as a percentage from 0 to 100%. So now that we've talked a bit about the different spectral bands that are available in multispectral dataset, let's see how you can correct the reflectance of those different spectral bands. First of all, why we need to correct the spectral the reflectance is basically because the lighting condition can change from one flight to the other, and you want to do some comparison between times. You need to make sure that the reflectance is on a normal base, so there's no effect on the lightning influence between the comparison between the different dates. So the goal here is to bring all the different flights to the same unit, as we can say. Also, on the same flight, one other thing that can change is basically the illumination of the flight. If you have a flight that lasts around 2 to 3 hours, maybe that's quite a big flight. Well, the sun can move, and also this will change the amount of light that can be reflected over a certain area, or also if there's some cloud that crossing or that going through your field during your acquisition. Well, those are all factors that can influence the reflectance of a pixel. So if you want to correct this reflectance, we support two different inputs. The first one is basically what we call the DLS, or the sun sensor. From MakeSense, it's the DLS. So it's a sensor that computes the sun irradiance over your scene during your flight, and also gonna keep all this information within the EXIF of the imagery, so we can correct for the sun position during the acquisition. The other reflectance tools that can be used, it's basically the reflectance panel. So the reflectance panel, it's gonna give you a correction for the reflectance in time, and in the time where you did your flight. So basically, you'll be able to have a different calibration for each of the individual band, and the panel should be the same throughout the time, so the reflectance can be quite similar. Or if you change some panel, you need to make sure that the albedo values that you will use will be consistent depending on the panel that you're using. So if you want to calibrate the reflectance of your multispectral project, you can use with Correlator 3D both sources together, or you can use either one of them depending on what you have. Also, what is the optimal overlap for multispectral processing? So basically, what we usually recommend for typical UAV project is having an overlap of 50% side lap, 70% front lap. But depending on the texture that you have on your images or the content of the imagery, the sun illumination, you can maybe raise this overlap between 60% side lap, 80% front lap, with some parallel flight line that's well enough suited with Correlator 3D. And this should help in order to find common tie points between all the images. So you'll make sure that you're gonna have a nice block, a stable block of images that will be able to correct the reflectance for it, and also generate some reflectance map and vegetation indices at the end of the workflow. And also, you can note here that we have, this is a Altum camera from MakeSense. We can note that we have five different sensor. And basically, the first step of the project is to register all those sensors together, which I will talk a bit later in this presentation. So now, importing multispectral data in Correlator 3D. How you can import your multispectral imagery in Correlator 3D. So here you can see the typical workflow of a multispectral project. So it's quite similar as a UAV project, but there's some specifications that are mostly focused on the multispectral data. The first one is before doing the aerial triangulation, the software will do a band registration in order to have one images stacked with all the different layers of a capture. So you're gonna have all the red, the green, the blue, the red edge, and the near infrared all stacked over together, depending on the band that you have. But you will be able to consider as this one images that perfectly align. From there, you will be able to perform your aerial triangulation once the band registration has been done. And then you can compute the typical output for a UAV project, such as the digital surface model, the point cloud, the digital terrain model, also the digital, and you can also edit your overall DEM. Before generating the ortho, it's at this point where the user will need to make a choice. Does he want to generate reflectance ortho or only classic ortho? So basically, if you want to perform a reflectance map or vegetation indices with calibrated reflectance, you will need to, prior to generating the ortho, specify the parameters of your reflectance panel or use the DLS sensor or the sun sensor that you have on your UAV during the acquisition. So this is basically the newest element that we've added to the multispectral workflow. Once the orthos are generated, the user will be able to compute a mosaic, edit his mosaic, and also export the final mosaic either as a standard mosaic, as a reflectance map, which is going to be a multi-band layer with 6 bands depending on the number of bands that you have, and each of the individual band will contain the reflectance value of every pixel. So it's going to be from a value to 0 to 1. Or you can also export your mosaic as a vegetation indices. So you can compute as many as vegetation indices that you want. And finally, if 3D model is required, you can also export, you can also create a 3D model from the surface model and the input imagery, and you can texturize the 3D models with all the different bands that you have. So now I've talked a bit about the theoretical part of the multispectral workflow. Now let's see how it translates into the practical side of the multispectral data. So as you can see here, we have the CORRELATOR 3D graphical user interface. So just a quick overview, but basically the buttons here are in a sequential order if you want to generate the complete workflow. So we have the create a new project, open a project, the automated workflow button, and then we have different modules one by one. But now, before starting into the modules, let's see how we can create a project from the multispectral imagery. I will go into File, New Project, and I will have a window like this that will appear. So basically, what I will need to do is I will need to select the UAV project, and really important to check the unregistered band. When you're working with multispectral cameras such as the Red Edge, the Altum, or even the Phantom 4 multispectral camera, you need to keep the numbers of camera as 1 because basically even if there are different sensors, at the end we're gonna have one images, so it's gonna be treated as one sensor, as one images. So you want to keep the number of camera as 1. If you want to see basically how the input data is looking, basically what we have here is we have all the imagery. So for each individual band, so for one capture, there's 6 bands that are taken. So I have the blue, the green, the red, the near infrared, the red edge, and also the thermal band. So my goal here will be to create one single image with those 6 bands in order to have one image at 6 bands all registered together. This is the first goal of creating your multispectral project. So once you have selected the unregistered band button, you will be able to click on Next, And here you will be able to add a specific folder where all your images are stored. In this case, I will add my first folder. And the software will use the timestamp and the name of the imagery to get the information from the metadata of the imagery based on the image name, and also will create my individual images. So as we can see here, I have all my images that is my first capture, so image 1. I have my 6 band here, and I can see the name of the different spectral band on the top. The next thing the user needs to perform is basically selecting what band he wants to use as the master band. So basically, the master band is the band that's going to be used as the master band. So all the band will be bringed out or stitched to this specific band. From our previous tests, we've seen that the green band is likely to be a good band to use as the master band. So in this case, I can select the good band, and also really important, trying to remember the order of your band here, because at the end, where you want to export the final mosaic, or you want to compute vegetation indices, well, you need to remember that the order is the order that you have specified here. So if you want to do the NDVI, well, it's going to be the NRI, the near infrared, and the red band. So it's going to be 4 and 3. At this point, you can also edit the band. You can change the name of the band if you want to, if you find it more easier, or you can also reorder the band if you need to have a specific order for your band. So once this is done and you have specified the good master band, you will be able to have here to import the exterior orientation parameters. As we can see now, I had previously 6 band, but now the name took the name of the master band. So now the green band will be the name of all my imagery. So it's all _2, which means it's my green band. If I would have chosen my red band, it would be _3. But in this case, since I've chosen the green one, it's going to be like this. So the software will go read the EXIF of the imagery and take the information. If you don't have this information written in the EXIF, or you have external orientation, you can also bring in a text file directly in the software. Then you will need to select the projection of your project. So in this case, I will use a classic UTM projection for this project, but you can also type in an APSG code if you want to look for a specific spatial projection. So once the spatial projection has been selected, you can see here the projection and also the dimension of each images, and then you will be able to click on next, and the software will read the metadata to get the focal length and the pixel size. Those are the 2 minimum requirements that you need in order to create your project. So here the focal length is the calibrated focal length that we can find in the EXIF data of the imagery. And then finally, the last step of the project creation is to select where you want to store your project. So in this case, I will leave it on my desktop. And I can see that my project was created. So at this point, I have created what we call a multispectral project. So I have here all my images and my camera and each of my flight lines. So in each of my flight line, I have all my different images. I also have the reflectance panel. At this point, none of them were inputted, but I will be able to later in this presentation show you how you can import your reflectance panel if you have them. One thing now, that if I look at the images of my project, I can see that my images it's kind of a bit blurry because my sensors are not aligned yet, which is gonna bring me to my next subject. which is basically registering the multiple band during the arrow triangulation. So first of all, why do we need to perform band registration during the AT? If we take the input imagery without the registration of the band, the type point that will be extracted will make no sense, and we'll just confuse the software because there's a spatial shift, a slightly spatial shift between all the different lands of my camera. So the first step that when you will launch the type point extraction is that the software will take an input imagery and register the band onto the master band that we have previously selected. And as you can see below, well, the output will be a 6-band. In this case, it's going to be a 6-band images that all my bands are perfectly stacked one after the other one, one over the other one. And from this imagery, I will be able to compute the type points of my project. So basically, how to perform the band registration during the AT, it's quite simple. The user only needs to launch the type point extraction, and the first step of the type point extraction will be to register the band together. So now, if we look what it gives once the project has been processed, I'm gonna open the project here. So as we can see here, I have a much more complete project, but if I open one thumbnail of the imagery, let's say around here, I can see now that my image is less blurry. So everything, all my bands has been registered together, and I have a nice images that ready to be processed. But this was done throughout the type point extraction. Once the type point extraction is done, you can already get some information about your imagery because you can visualize without even correcting the reflectance. You can visualize quickly your images and see what kind of feature that you have. But you can also create, in this case, some composite color imagery because I have 6-band here, and I can edit. The image band setup. So basically, this bringing me to my next subject, which is viewing the different bands within the software. So once the type point extraction has been done, you can quickly verify if the adjustment that was performed on the images was okay. If you still think that there's a slightly offset, you can try a different master band, but as we've previously tested with the software, the green band should usually give good results, but it's always case-by-case project. So if you want to assess the band registration quality, you can switch from one band to the other one quickly with the thumbnail of the imagery. So if I show it to you like this, so we're gonna have here the different 3-band imagery, but I can change the order of the band. So let's say if I want to see a composite color imagery, I can put the near infrared in the red channel, the green channel in the red channel, and then the green in the blue channel. It's kind of a misinterpretation here, or it's kind of a weird, or it's kind of hard to understand, but this will give me more information about the vegetation. First of all, it's going to give me quickly information about the health of the vegetation, since specifically the trees has a good and healthy trees is going to have a higher reflectance in the near infrared, and if the trees has not a good health, you will see that the red will be less bright than a healthy tree. So you can quickly visualize it. You can quickly just visualize it over those imagery. So you can you can then see all your imagery quickly like this, and you can also go channel per channel like this. 1, 2, and you can see that there's at least no spatial shift between all the imagery, so they're all perfectly aligned together. Also, at this point, when you launch the arrow triangulation modules, you can also assess the tie points of your project. So you can see all the little white lines here are corresponding to common features that we have found between the imagery. So once you have registered all your band and you have done the initial tie point extraction, you're gonna have something like this. And from there, you will need to refine the position and the camera orientation with the bundle adjustment. So basically, for typical multispectral data, you should leave the parameter as they are here. So the EO at unconstrained, the sensor calibration at unconstrained, and also if you have some ground control points, you can use them as a ground reference. The ground control points can be imported as a text file within your project. So now that you have done your aerial triangulation, you can then, and you're satisfied with the result, you have two choices. You can either already bring in the reflectance panel if you have access to them, or you can generate your surface model, terrain model, and then bring in the reflectance panel within the software. So you have the choice, but the panel needs to be imported prior to generating the ortho photos if you want to have some reflected orthos. Now let's see how you can import those reflectance panel. So you can have multiple panel within your project. So you can have a panel that was taken at the beginning of the flight, and also a panel that was taken at the end of the flight. Or also you can have a panel that, let's say, you're performing 2 flights and you need to do a battery change at the middle of the flight. You can take a panel at the you can have a panel at the beginning of the flight, one in the middle when changing the battery, and one at the end. And all those panel will be integrated over time during the reflectance calibration. So it won't only be the beginning or the end panel that will be used. So this is what we've found the most efficient way. So to do a reflectance calibration over the time of the flight, which usually gives the best result for reflectance calibration. So as you can see here, if I'm showing to you right away, we're gonna have here all my panel. So I have my six band. So I see my panel from each of the individual channel or band, and you can import those images within the software. So the first step will be here under your project, in your project tree. You're gonna have the reflectance panel and the Mica Sense camera. So you can add a plus button here, and it will bring you a calibrated reflectance panel window. So basically, you will need to specify the ID of the panel. You can call it, let's say, before, after, or middle, depending on the naming convention you want to do. It's just basically to remember what is this when this panel was taken, when you're gonna. So yeah. So once, let's say I've done before, I could then import all my different images here. So I'm gonna go here and I'm gonna add all those imagery within the window, and I can see now that each of the panel was associated with the individual band at the beginning or channel. One other thing you will need to perform is you will need to type in the reflectance value of your panel. So basically, for most of the panel, the reflectance value should be um, should be uh, should be included within your panel. So if I take a look here on the panel, I can see. I will show it to you. I can see here if I open. I can see here that the value will be written here. So you can have all the albedo value for each band. So those value will need to be inputted in the software. So here, as you can see, we have the different reflectance value for each of the band. Once those have been inputted, you can then click on next, and you will be able to pinpoint the center of the panel, and the software will automatically detect the areas of interest or the region where the calibration needs to be taken from. You can also, if you want, you can also adjust those little markers that they fit in the panel over here. So once this is done, you will need to do it for all of the different band. But once you will do for the first one, it should automatically detect all the other one. So it's just to verify that they were correctly identified. Click on next. And then once this is done, I will have my panel here in my project tree. I can also add another one and call it, let's say, after, where it can be the reflectance panel that I've used at the end of my flight, or at the middle of the flight. The other options that the user can have for the reflectance calibration is the use of the sun sensor. So the sun sensor is a sensor that is integrated on the UAV that basically registering or memories the position of the sun and the lightning condition for this specific day of flight. So you can use for the reflectance calibration both of them. So you can use the reflectance and the sun sensor together. If you only have the reflectance panel, you can use only the reflectance panel. Or if you don't have some reflectance panel but only the sun sensor, you can use only the sun sensor. So if you want to choose which one you need to select for the reflectance calibration, it's at the ortho rectification step that you will do. So once you have imported your reflectance panel, if in this case it was probably before the DSM generation, I can then jump into the DSM generation. So by default, the software will generate a raster surface at 5 times the ground sample distance of the imagery. But the user can also specify the different resolution. So you can take maybe the maximal resolution and multiply it by 3. So it's all really depending on the output that you want to perform. Also, you can generate a point cloud if you want, but the point cloud is optional. What we really is necessary is the raster surface model. So as we can see here, once this is done, I will have something like this. So I will have a digital surface model of my area. I can use this digital surface model to directly generate my orthos. So it's going to be true ortho based on the surface model. Or I can perform what we call the DTM extraction. So it's an automatic tool that's going to remove as much as possible all the elements that are not ground related, such as trees, buildings. In this case, it's more trees, but it will try to remove as much as possible all the elements to have a smoothed surface to perform the ortho rectification from it. You can also perform some DEM editing on your DSM or DTM. But since this is not the goal of my presentation, you can maybe go on our website and we have a specific webinar on how to generate highly accurate DSM and DTM, which is going to give you a bit more information about those subjects. So once this is done, you can then start the ortho rectification, and you can see here that I have the two options. So in this case, I had the sun sensor, the DLS sensor, and also the calibration panel for this flight. So I can use both of them. So when I will launch the ortho rectification, it will create one ortho image for each input image that is corrected for the reflectance. But if you want to do some tests and maybe you want to see the difference between only the calibration with the panel and only with the sun sensor or both of them, a good approach to have is to manage the ortho and the mosaic folder, because once an ortho folder has been inputted and also a mosaic folder has been inputted into the software, you can change the directory if you want to store the output into a new directory. So I can do a first run of ortho with the ortho that are corrected with all the information, so the reflectance panel and also the sun sensor, and also I can then change with the little plus button here the ortho folder, specify a new ortho folder, and regenerate the ortho with, let's say, only the sun sensor. If I want to compare what is the effect of the panel for the calibration purposes. It's the same thing with the mosaic. So if you want to generate a mosaic with both of the reflectance calibration, so the DLS and the panel, you can select here in the ortho folder the ortho that contain both information, and then generate the mosaic. Then you can change the ortho folder, change the mosaic folder, and regenerate the mosaic with only the orthos that were corrected with the DLS sensor. So this is all information that is good to know before overwriting a result. Because if there's an ortho folder that's already in there, and there's some ortho and ortho photos in there, and you launch another ortho rectification, it will overwrite the actual ortho that are stored into the ortho folder. So once the ortho has been loaded, you can either browse them in within your map, but you can also create a mosaic. So basically, we found that the optimal parameters should be left as they are here. So you can maybe change the feathering size depending on the type of element you're trying to map. And also keep the color balance, keep everything balanced. So we're gonna do a color balance for the reflectance based on the images that are looking at the same point. And also you can use the nadir optimization option for UAV project. So once this is done, you're gonna have a mosaic that's gonna contain all the different channels. So the red, the green, the blue, the near infrared, and the red edge, and you can use this information to compute some vegetation indices. So if you want to compute some vegetation indices, The minimum requirements are usually having four band, depending on the camera that you have. So red, green, blue, and at least the near infrared to perform the normalized vegetation index. So basically, the NDVI, it's a ratio between the near infrared and the red band, but as a downside, it can suffer where the vegetation is quite dense. So around 0.7, the NDVI should tend to cap off. So there's other vegetation indices that can be more or better suited if you have dense vegetation in the in your area that you're trying to map. So basically, if you want to use the number the NDVI, it's gonna quickly give you an overall average or an overall content of where is the vegetation on your area. It's the most common vegetation indices used. It also can be used to difference the soil water availabilities in the vegetation. And so yeah, there's some other vegetation indices such as the normalized different red edge index that have more effect on the chlorophyll of the plant. So you can use this instead of the normalized instead of the near infrared band. It can be used with the red edge band, and all those vegetation indices can be computed within the export mosaic option. So if you want to export an NDVI or another vegetation indices, you can go into File, here, Export, and Export Mosaic. So now you're going to have a window like this that will appear. The first mosaic type, which is the it's the standard one, it's going to be an RGB mosaic. Or you can export, if you have done some calibration reflectance, you export a reflectance map. So it's going to be a geotiff with multiband, multi-channel geotiff that will be generated. And this will include all the different bands stacked one over the other one, stored in a 32-bit float with a value from 0 to 1. You can also tile this with, let's say, a shapefile, or you can also crop with a shapefile if you only want to export a small section of the area you're trying to map. If you want to compute some vegetation indices, you can use the little index window here, and you can then change the setting. So we have already a preset vegetation indices, but the user can also create his own vegetation indices in the case where it is not here. So I can, let's say, wipe this like this and use a custom vegetation indices, and I could say, let's say, if it's just a roughly example, I can add A plus B, which is a simple addition, but I can then select what band I want as the variable A and at the variable B. And as soon as I'm adding a variable here in the formula, well, I can specify this I can change the band for the specific variable. If you want to export an NDVI, so let's say here, I'm going to choose the simple NDVI, and the near infrared is the band 4, the red is the band 3. So I can use it like this, and then I can export as a floating point option. So it's going to create a single raster layer, which here you're going to need to specify the node data value that you want. So you can leave it as it is like this, and this will compute a geotiff, a single band geotiff that you can then import into a GIS software to perform more analysis. So you can use, let's say, maybe QGIS or all other GIS software. So you can do this with a wide varieties of vegetation indices and also your custom one. So basically, what are the competitive advantage from calibrating the radiometric reflectance, in Correlator 3D? Well, the first main advantage is we're taking the integration of the reflectance panel over the time. So if the user has, let's say, 3 panels, one at the beginning, one at the end, one in the middle, we're gonna take an integration of those reflectance information and try to integrate that to the reference, to the reflectance correction. So the reflectance will reflect the lighting condition of the flight. We also have a better color balancing for the reflectance mosaic. So this brings me also as the seam line editing. So the seam line creation is what we call it's an intelligent seam line creation versus a simple averaging between all the individual ortho that are on the same pixel. Also, our reflectance mosaic is a multi-band reflectance mosaic, so it's not going to be individual band, individual channel exported. It's going to be one file with all the channel inside this this file, and also with the Altum, we're going to integrate the thermal imagery. Also, the reflectance value are stored into 32-bit instead of 16-bit for other competitor. So this is a main advantage because you don't lose any information or you don't need any other calculation with the reflectance value. As soon as you're exporting your reflectance map, you're gonna have the real reflectance value. So finally, a few unique benefits from Correlator 3D. We have unmatched processing speed, since most of the processing is done on the graphic card and also on the SSD drive. So these are the two main components we usually focus on, as well as also the CPU. We offer a solution for a wide range of customers, from the one-button click solution to the module by module option. We can process unlimited numbers of images on a single standard PC, even if Multispectral has a lot of imagery, because all the individual channels are at beginning stored on individual images. And also we can batch process within command line, and the software can be installed on some cloud service such as AWS or Azure. We offer also different types of licensing, from the monthly, the yearly, the permanent license. We also have different types of licensing. For the multispectral, it's usually going to go with the UAV license, but we offer options for medium format satellite data and also full format data. And we also offer node lock and floating license. So again, we offer free processing for marketing purposes. So if you want to see what you can get with Correlator 3D, feel free to write us at sales@simactive.com or download your free trial at www.simactive.com. Thank you everyone for joining this online training session. So my name was Simon Grandin, and I hope you have a great rest of the day. Thank you.